Hello, my name is Gabby Clark, and this is my Lab 1 presentation. In this lab, we conducted an experiment that tested Newton's second law of motion, which relates the net interaction between the system and surroundings to the observed motion of the system. We did this by filming and observing the position of an everyday object moving at a constant speed without changing direction, then compared it to our predicted position on a computational model. I observed the motion of a vitamin bottle rolling across a table at a constant speed. As you watch the video, you will see several red diamonds along the object's center of mass as it rolls across the table. These red diamonds track the object's position along certain time intervals as the time approaches 2 seconds. By looking at the graphs on the side, you may wonder why the y-axis is not a straight and constant line. This is because I could not place the tracking points in a straight line across the y-axis. However, for this lab, the y-coordinate isn't our main focus. The main focus is the position of the bottle along the x-axis. So, what if the axis were flipped? If the origin was to the right of the object and the object was approaching the negative x value, the graph would be flipped. By flipped, I mean instead of the line approaching upwards from the origin or having a positive slope, the line of the new graph would start at the origin and approach downwards, or would have a negative slope. This is because of the way that we graph the position of the objects, which is whether they move away or towards the origin. If they move away from the origin to the right in the positive direction, the position would be positive. If the position was going to the left or being negative, the position value would be negative. So next, I made a computational model. So the bottle's mass was 0.39 kilograms or 39 grams. And since the bottle's starting at the origin, the initial position vector is 0, 0, 0. For the bottle's velocity, I calculated the change in velocity over the change in time. I used the first entry point and the last entry point as my values to get this number. And because the bottle's velocity is constant and non-changing, Newton's second law isn't needed for this step. However, we need Newton's second law to predict the change of position over the certain time intervals. In this case, my delta t was 0.1. Running the final code. The reason why the graph moves so fast is because I chose my delta t to be 0.1 instead of 0.001. I chose 0.1 because it made it easier to graph and compare the tracker data versus the glow script data on the next slide. As you can see, not only the position is constant, the velocity is constant as well. And so the reason why the velocity is constant is because we only use one velocity, which is why we didn't need Newton's second law for that step. By looking at the individual graphs on the right, you can see that the glow script graph, or the graph on the top, looks almost identical to the tracker graph, or the graph on the bottom. The only difference is, along the tracker graph, there are minor inconsistencies of the speed of the object. This is because in the glow script graph, we assume that there are no forces acting upon the bottle, while in reality there are multiple pushes and pulls or forces acting upon the bottle, like friction or minor bumps on the table. This caused the force upon the object not to be zero. It's not 100% possible to say every small push and pull that acts upon the object. However, through general assumptions and previous lessons, you can get an idea of majority of the forces. In other words, the predicted position of the object is constant, while the observed position is not. So in order to move these two positions closer together on the graph, you'd have to calculate and update the position for every time interval at very, very small intervals. For example, we could have to take the difference of the velocity over time, 0.0001 to 0, and then the difference in velocity over the time interval 0.0002 minus 0.0001, and so forth and so forth. So basically, the closer the time intervals are together, the more accurate and closer the two data points will be. Thank you for watching my lab video.